Hey everybody, Chris McClure here. We're going to now talk about graphing equations involving two variables. And we'll typically use x and y as our two variables, but we could just as well use any other two letters of the alphabet, any other two variables. So graphing equations by plotting points. So what are we talking about here? Well, we have an equation involving two variables. We need to find pairs of values for the two variables, x and y, that will make the equation true. So what we're talking about is for x squared plus y squared equals 5, for example, is finding two numbers, one for x and one for y, that will make the equation a true statement. So for example, if x is 1 and y is 2, well, 1 squared plus 2 squared is equal to 5. Then that's a true statement. So 1 and 2 will be two numbers that satisfy the equation. Also, negative 1 and 2 will satisfy the equation because negative 1 squared plus 2 squared is 5. Also, 1 squared plus negative 2 squared is 1 plus 4, which is 5. So 1 comma negative 2 is also another point that satisfies the equation. Also, negative 1 and also negative 2 for negative 1 for x and negative 2 for y will satisfy the equation. So, and there's going to actually be infinitely many pairs of x and y which satisfy the equation. And our goal is going to be to graphically display all the points, all the pairs of x comma y which satisfy the equation. And that graphical display is just really called the graph of the equation. Same thing for all these other equations relating the x and y variables to each other. Okay? So here's an example of a graph. And the reason that we like graphs is that they tell a picture. They tell a story, I mean. We people are usually visual thinkers. If we can visualize it, then we'll be better able to understand the relationship between the x and y variables. This particular example here really shows the relationship between risk and annual return for some sort of investment. Maybe it's a mix of stocks in a particular portfolio. And imagine what the level of risk versus the return rate is according to the different balance between U.S. stocks versus foreign stocks. If you have 100% stocks in your portfolio, then you might have this particular balance between risk and return, about maybe a 15.2% level of risk and maybe a 14.5% annual rate of return. But you can see as the percent of foreign stocks gets increased from 0 to 100%, we see this trajectory of risk versus return, so that it kind of minimizes the level of risk here at the 30-70 split with annual rate of return about 15.9%. And then once you go beyond 30% foreign in your portfolio, you continue to increase your annual rate of return, but you're also greatly increasing your risk. That's the sort of story that I could tell just by looking at this graph. That's why we like graphs, instead of just looking at a bunch of numbers or looking at an equation. So we're going to talk about graphing equations. In order to do that, we first need to talk about does a point satisfy an equation? In other words, is a point on the graph for that equation? Now, when we say a point satisfies an equation, we're really not speaking entirely correctly. When we say that a point satisfies the equation, what we really mean is, does that value for x and value for y satisfy the equation? So when we're talking about 0, 4, does this point satisfy the equation negative 3x plus y equals 6, which is the same thing as asking, is this point on the graph of this equation? We're all asking, really, when you plug in 0 for x and plug 4 in for y, is the equation a true statement? And indeed, when we plug 0 in for x and 4 for y, we get 0 plus 4 on the left-hand side, and on the right-hand side we have 6. And it's not true that the equation holds. So for this particular pair of values for x and y, 0, 4, the equation is not a true statement. So this point in A there does not satisfy the equation. What about the next point? Negative 2, 0. Well, you plug in negative 2, and you plug in 0 for y, and 6 plus 0 really is equal to 6. So negative 2, 0 works. It's on the graph. How about negative 1, 3? Plug in negative 1 for x, 3 for y, and you get 3 plus 3 is equal to 6. And that also shows that this point is on the graph. It satisfies the equation. Okay? So when you plug in the value for x and the value for y, we see that that pair satisfies the equation. Then we know that that point is on the graph. And indeed, here's, well, this point right here is at 0, 4. That was this first point right there. Here's negative 2, 0 right here. And this point right here is negative 1, 3. And notice that those 2 points are on the graph. And the blue line is the graph of this equation. The equation will imply that there's an infinite number of pairs of values for x and for y. After all, you can specify some fixed value for x and find the corresponding y value. You want to see how? Well, I could take the equation and add 3x to both sides. Aha, y equals 3x plus 6. So if you tell me a value for x, then all I need to do is multiply by 3 and add 6, and then I'll have the corresponding value for y. And because x could be any real number, then y will be an infinite number of numbers as well, according to whatever x is. Okay? So let's go ahead and talk about graphing an equation. It's really a matter of coming up with a couple of points that are on the graph, and after you plot 2 or 3 or 4 points, and then you draw a line or some other curve through the points, like playing connect the dots. So let's take a look at the graph of y equals 2x plus 5. Alright, so we can specify some different values for x, like 0 for example, and then find the corresponding value for y. Now if x is equal to 0, 2 times 0 plus 5 is 5. So 0, 5 is going to be a point on the graph of the equation. Maybe we can set x equal to 1. And if x is 1, then y is going to be 7. And 1, 7 is going to be on the graph. And likewise, if x is equal to negative 5, we'll see that y is equal to negative 5. So we have yet another point on the graph, and yet another point. And then we plot those points on the xy axis. And then we draw a line through those points. We can just slap down a ruler, line up the ruler along those points, and then draw a line that connects those dots. Okay? And that blue line is the graph of this equation. All right, here's another example, y equals x squared. So we can go ahead and figure out some points that are on the graph. We can go through and specify these different values for x, maybe from -4 to +4. And of course, square each of those numbers. So we have this whole list of ordered pairs whose x and y coordinates satisfy the equation. Then we could plot those points on the xy plane, like you see here, those black dots, and then connect those dots with that blue curve, which, by the way, the shape of that blue curve is called a parabola. Parabola. Okay, so now we're going to look at some more advanced techniques in graphing an equation beyond just plotting a whole bunch of points and connecting the dots. We're going to look at some particular points called intercepts. And what an intercept is where the graph crosses one of the coordinate axes. So, in other words, where does the graph cross the x-axis? It could be in one or two or more places, and those will be the x-intercepts, for example. So right here we've got this blue graph here, and notice that where the blue graph crosses, or at least intercepts the x-axis, we call that an intercept, x-intercept. And we also have x-intercepts here and here as well. So those three circles identify the three x-intercepts. Notice that the y-coordinate for each of those x-intercepts is going to be 0. So that should tell you, if you know the equation that this graph belongs to, then you can get the x-intercepts by setting y equal to 0 and solving for x. And likewise, we have the y-intercept there, where the graph crosses the y-axis. Notice that the x-intercept there is x equals 0. Here we've got this crazy graph here. Notice that we have x-intercept at -3, 0 right here. An x-intercept at 3/2, 0. An x-intercept at 4.5, 0. We've got a y-intercept at 0, 3, at 0, -4/3, and also at 0, -3/5. Now, if we have the equation, let's go ahead and do what we said. To find the intercepts, we can set the y variable equal to 0 and solve for x to get our x-intercepts. And if we want to get our y-intercepts, we can set x equal to 0 and solve for y. Okay? So that's what we're going to do. Now, as an example, suppose that we've got y equals x squared minus 4. Let's find our x-intercepts and our y-intercepts. So let's go ahead and first let's plot some points. Here's some points. Here's some values for x. Here's some values for y. And we've got a list of values of ordered pairs. Also, we could set x equal to 0, and if x is equal to 0, we have y equals -4. So 0, -4 is going to be the y-intercept. We could set y equals 0, and if y equals 0, we have x squared minus 4 is equal to 0. That means that x squared is equal to 4. That means x is equal to plus or minus 2. So we have 2, 0 and -2, 0 as our two x-intercepts. And voila! We've got the graph of x squared minus 4. Y equals x squared minus 4. We've got our two x-intercepts right there and there. We've got our y-intercept, and we've got several other points that we got from a table that we created. Now, truth be told, that for the graph of y equals x squared minus 4, we know that that graph is going to be, or have the shape of, a parabola. It might not necessarily be obvious to us that it will look exactly like this, but at least we know what the general shape is. But look, here's the thing. We've got 3 points right here. And we know that there's going to be a certain amount of symmetry. And as we're going to soon learn soon, when we look at graphs of second degree polynomials, well, the graph is going to be a parabola that opens upward or downward if it's the x variable that you have powers of within the expression for the second degree polynomial. It'll be upward if the leading coefficient is positive, and the graph will open downward if it's negative, for example. Anyway, let's move on. Now that we know a little bit about intercepts, x-intercept, y-intercept, now let's talk about symmetry. Symmetry is going to be very useful for us. If we know that the graph is symmetric with respect to one axis or some other axis or both axes, then all we would need to do is plot a couple points in one quadrant, for example, or 2 quadrants, and then use symmetry to plot the other points, for example. Now, we could have symmetry with respect to the x-axis. And what that means is that the x-axis would act kind of like a mirror. So if you see the graph as it appears above the x-axis, then you will see the absolute mirror image of it below the x-axis, kind of like what you see here. And in particular, if you have some point on the graph with coordinates x comma y, then you know that x comma negative y is also on the graph. Now, this is not the graph of a function, mind you. Remember, a function, for each value of x, you need to have only one. You need to have one and only one value for the y coordinate. But that's okay. This is still the graph of some equation involving x and y. So in this case, we have symmetry with respect to the x-axis. So all you would need to do to check to see whether you have symmetry with respect to the x-axis is just replace y by negative y in the equation. We'll see an example here soon. So suppose that we have the graph of some equation and 3 comma 2 is on that graph. Graph is symmetric with respect to the x-axis. Well, that means 3 comma negative 2 will also be on the graph. Mirror image across the x-axis. So there we go. Now, we could have symmetry with respect to the y-axis, in which case the y-axis acts as a mirror. And if you have some point on the graph with coordinates x comma y, then negative x comma y is also on the graph. So if 3 comma 2 is on the graph, then 3 comma negative 2, excuse me, negative 3 comma 2, I should say, negative 3 comma 2 is also on the graph. You could also have symmetry with respect to the origin, which basically means is if you have some point with coordinates x comma y on the graph, that the point negative x comma negative y will also be on the graph, and that the graph will be symmetric with respect to the origin. So if 3 comma 2 is a point on the graph, and the graph is symmetric with respect to the origin, then guess what? Negative 3 comma negative 2 is also on the graph. So how do you test for symmetry? Well, you can test for symmetry with respect to the x-axis by replacing y by negative y. And if you get the same equation, then hey, your graph is symmetric with respect to the x-axis. You could test for symmetry with respect to the y-axis by replacing x by negative x. And if the equation that you get is the same as the original one, then there you go. You have symmetry with respect to the y-axis. If not, then no, you don't have symmetry. And to test for symmetry with respect to the origin here, replace x by negative x, replace y by negative y, and if you get the same equation, then you have symmetry with respect to the origin. So let's go ahead and take a look here. This basically summarizes everything that we just said. Moving along here. So let's do a couple examples here. First, suppose that we have the equation y equals x squared minus 9 over x squared plus 2. Let's test for symmetry. First, let's test for symmetry with respect to the x-axis. Replace y by negative y. And then do we get the same equation after you simplify? And the answer is no. Okay, so we know that the graph, and we don't know what the graph looks like yet, but we know that it's not symmetric with respect to the x-axis. Now let's test for symmetry with respect to the y-axis. Replace x by negative x and simplify. Now negative x squared is x squared, both in the top and the bottom, so you really do get the same equation, because this equation here is exactly the same as the original one. So this tells us that the graph for this function will be symmetric with respect to the y-axis. And finally, let's test for symmetry with respect to the origin. Replace x by negative x, replace y by negative y, and simplify. And do you get the same equation? And the answer is no. So that means that the graph of this equation is not symmetric with respect to the origin. All right, moving along here. And indeed, we have a snapshot. This is from a graphing calculator. And as a matter of fact, I could show you how to graph that. If you've got a TI-84, I'll show you how to graph that. Let me pull out my TI-84 and clear that. All right, so let me pull this up real quick. That is x squared minus 9. We use parentheses, x squared minus 9, close parentheses, divide that by, and then the denominator, we have x squared plus 2. So x squared plus 2. Now, hold on. I realized that I made a mistake here. There's my x squared plus 2. There, right, so now let's go ahead to our window so we could set our viewing window. And maybe let x go from negative 5 minimum to positive 5 by 1s. And also maybe negative 5 to positive 5 by 1s. And indeed, there is the graph. We see that it is symmetric with respect to the y-axis, but not symmetric with respect to the x-axis, nor with the origin. Okay, here we go. Let's talk about graphing some key equations, and in particular, we already talked about y equals x squared, so now let's talk about y equals x cubed. Y equals x cubed, which we call the cubic we're going to try to find the intercept, test for symmetry, and plot some points when we graph this equation. So first of all, are there any intercepts? Well, set x equal to 0. And when you set x equal to 0, what is y? Y would also have to be 0. And when you set y equal to 0 and solve for x, then x is equal to 0 as well. So you have one and only one intercept, and that's at the origin. Okay? Now let's test for symmetry. First, is this graph symmetric with respect to the x-axis? Well, replace y by negative y. And when you do that, you get negative y equals x cubed, which is not the same as the original equation, y equals x cubed. So we see that there's no symmetry with respect to the x-axis. To test for symmetry with respect to the y-axis, replace x by negative x. And when you do, you get negative x cubed, which is negative of x cubed, and y equals negative x cubed is not the same as y equals x cubed. So we see that this graph is not symmetric with respect to the y-axis. Finally, let's test for symmetry with respect to the origin. Replace x by negative x, replace y by negative y, and simplify. Now, negative y is going to equal negative x cubed, which is negative of x cubed. And then you can cancel negatives on both sides, so you got y equals x cubed, which is the same as the original equation, which tells us that the graph is symmetric with respect to the origin. So all we need to do is just come up with a couple of points, maybe in the first quadrant, maybe let x be equal to 0, 1, 2, and 3, and cube each one of those. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. So we've got these 4 points that we could plot, and indeed we got 1, 2, 3, and if we want we could probably plot 3, 27, except that'll take us, here's 3, and we'd have to go way up here to plot 27. But we don't need that because we can just get the general shape by plotting this point, and this point. But because of the fact that the graph is symmetric with respect to the origin, then we know that, look, if 1, 1 is on the graph, then negative 1, negative 1 is also on the graph. And if 2, 8 is on the graph, then negative 2, negative 8 is also on the graph. So we can go ahead and plot those points. And then draw a nice smooth curve going through those points. And voila, we've got the graph of y equals x cubed. For example, how about this equation here, x equals y squared? Let's go through the same process. We'll just go through a little bit more quickly. Let's test for intercepts first. Replace x by 0. Solve for y. You get 0. Replace y by 0, solve for x, you get 0 as well. So again, we have the origin as the one and only intercept. And then test for symmetry, replace x by negative x, and you don't get the same, so it's not going to be symmetric with respect to y, but you replace y by negative y, and you still get x equals y squared, because negative y squared is y squared. So this graph is going to be symmetric with respect to the the x-axis. And if you replace x by negative x, replace y by negative y, you get negative x is equal to y squared, which is not the same. So it's the graph is not going to be symmetric with respect to the origin either. So only symmetric with respect to the x-axis. So you can come up with a couple of points, values for x. So if x is 0, when y is 0, if x is 1, then you have y squared is equal to 1. That means that y is equal to plus or minus 1. And if x is 2, then y is equal to plus or minus square root of 2. Well, plotting square roots is not very easy, is it? Well, we can let x be equal to 4, because 4 is a perfect square. That means y would be plus or minus 2. And if x is 9, because we know 9 is a perfect square, then x will be plus or minus 3. And indeed, we can even take this equation and solve for y and take the positive square root of x. So we can draw the graph of square root of x. As a matter of fact, we can draw first the positive square root of x, and then draw the graph of negative square root of x, which would be the reflection across the x-axis. Anyway, moving along here. So that's what we did here. We drew the graph of y equals square root of x. We saw that the origin was the one and only intercept, and we let x be equal to some different values to try to solve for y, but that doesn't work so well because y equals square root of x. So it'd be better for us to let x be equal to some perfect squares, like 1, 4, and 9, which is the first 3 perfect squares, so that we get y equals 1, 2, and 3. So we plot those points. So we've got the graph y equals square root of x. And then take the negative of that, because we know that the graph is going to be symmetric with respect to the x-axis, so we have the reflection about the x-axis. Okay? Let's draw the graph y equals 1 over x. Let's graph this equation. So are there any intercepts? If you let x be equal to 0, you can't do anything with that because you cannot divide by 0. If you set y equal to 0, can you solve for x? And the answer is no. Because you cannot take 1 divided by anything and get 0. So there aren't any intercepts in this case. Now let's check for symmetry. If you replace x by negative x, you don't get the same thing. If you replace y by negative y, you don't get the same thing. But if you replace x by negative x and replace y by negative y, you end up with y equals 1 over x. So that means that there is symmetry with respect to the origin. Then you can plot a few points. Then you could plot a few points. Like, for example, you could let x be equal to some different real numbers. Find the corresponding values for y. If x is 1/10, then y equals 10. Or if y equals 10, x equals 1/10, for example. So get some different ordered pairs for x and y. So you get these points that you can plot in the first quadrant. And then, of course, you could take the negative x and negative y for all those points and plot those corresponding points in the third quadrant. So we have that symmetry with respect to the origin. Okay? And that's it, folks. When we come back next time, we will talk about graphing equations of linear functions. Which are lines. All right, now, this weekend I'm going to go on a trip. In fact, I'm leaving on Sunday. So I'm probably going to come into the office tomorrow, which is Saturday, and long enough for me to record another lecture and post some homework for you to look at. Now, today is Friday, June 14th. So most of you are aware, in fact, all of you should be aware, that there is a chapter R quiz. Many of you have already taken it, but some of you still haven't. Procrastinators, sorry, I don't mean to bash the procrastinators. Sometimes I do it myself. But you need to get that quiz done by midnight tonight. That means start no later than 10:30 p.m. this evening, okay? And then I've also posted the Chapter 1 quiz. So make sure that you work through the Chapter 1 material and take the Chapter 1 quiz whenever you can. And, of course, the due date appears on Blackboard. Okay? Also, someone emailed me asking me about the homework for section 1.7. Well, there must have been some technical snafu. I really did post it earlier a couple days ago, but apparently it went away. So, and I don't know what happened, but I went back and reposted it just a little bit ago, earlier this afternoon on Friday, June 14th. Okay, but as issues come up, let me know. Now, I'm going to be traveling to South Carolina, and I'll be gone for 2 weeks from my physical location, but I'll still be keeping up the same schedule and recording lectures and stuff. So virtually nothing has changed, except I won't be here physically in Iowa until the weekend of the 29th and 30th later this month of June. Okay? All right, everybody, take care, and I'll see you next time.